Hey guys, today I'll be sharing about integrating area under the curves, and this is my infographic lesson on how to deal with such a mathematically abstract concept. I have a great hack for dealing with this concept of integrating an area, and I would like to begin by saying that integration to many people is like the evil clown. It is cynical, it is creepy, it is scary, and it is not especially funny for the people involved. If you look at a simple example like this, you will realize that you have three separate areas to deal with and you have no idea how to find whether or not you're on the right track. But what if I tell you that there is a seemingly easy hack to get around this problem? My way of dealing with this is to actually use houses from around the world to simplify the concept of integration. And you might be thinking that this is going to be a crazy idea because buildings are all different. But I'm going to show you in a while how this is working. Since you are thinking that there are so many buildings around the world, and in fact this is true, I'll let you Google any building in the world and see for yourself, and we'll check back again in a couple of minutes to put back together all the different buildings that you have found. And we'll go around the room to have a share of what are the different buildings that you have found. With the power of the internet, 5 minutes have passed, and all of you should have come to the conclusion that all buildings on a two-dimensional plane should have a roof, a floor, and two opposing walls. This is my story of the three billy goats and the troll. For the troll, even despite the fact that he's living under a bridge, this qualifies as a shelter in some way, as you can see, because he has a red roof, blue floor, and two walls. And this is the concept that we'll be using for integrating area under the curves. A curve will always have a roof, a floor, and two walls, which we call the upper and lower limit for integration. And you will realize that the roof, floor, and two walls will subtend any finite area, which is also known as the integral. Even a TP, as you might say, has no walls. But if we have a closer look, the walls, the floor, and the roof are actually all intersecting at the same points. And by eliminating the TP and embedding another graph on a Cartesian plane, you will be able to see that these intersection points correspond to the x and y intercepts. And there you have it. From a very basic integral, we can see that horizontal lines correspond to the roofs of the buildings. Another horizontal line corresponds to the base of the buildings, and that each building has its own specific set of walls. And this allows you to find the area between the curve and the graph and the axis. A difficult question like this will involve a roof, which in this case is the axis, the curve, which is below the axis, but even so, you always have the two walls, which are your x values, and this as well corresponds to a shelter, just like an underground cavern. For a more difficult question, such as finding the area of a semicircle, we are coming back to revisit the same points of how the curve, the floor, and the walls intersect at the same points. And once again, you'll be able to see that it also corresponds with a glass dome, which is also a common feature of a building in our world. And once you have embraced the concept, you can mix out this thing as much as you like and look at the area of the curve on the y-axis instead. This is your roof, that's your floor, and these are your two walls. By tilting your head 90 degrees to the right, you should be able to see the equation of the curve, equation of the floor, and don't forget that you have 1 and 3 as your upper and lower limits. I would not recommend this for mathematical purists, but rather more for students who are starting integration for the first time and who probably need some attempt to master the concept. Apparently, it works, so good luck and all the best with using this concept. Stay awesome.